In this example, we have a rigid bar BDE. The bluish BDE is supported by two rods AB and CD. The rod AB is made of aluminum, which has a lower modulus of elasticity and has a cross-section area of 500. The rod CD is made of steel with a higher modulus of elasticity and a larger cross-section area. So for the P equals 30 kilonewton added downward to point E to determine deflection of B and E. Okay, we're calculating delta B, delta E, and in the process you will also need to know delta D. Okay, these are the three things we're calculating. How do we calculate delta B? How do we calculate delta B? Since point B is connected to is just closely tied to the rod AB, right? There's no gap between them. So the deflection of point B will be equal to the deformation of AB, right? So in the same way, delta D equals the deformation of rod CD. How can we calculate these two? Here, you just need to know F AB, LAB over EAB, AAB. Right? So the L has been given, A has been given, E you have known, so you just need to find out what is the F. Right? So in the same way here, you just need to find out FCD, LCD over ECD times ACD. Here the only unknown is the FCD. Okay, so if we can determine FAB and FCD, then we can solve these two components, right? How about after that? Based on that, how can we calculate delta E? How can we calculate that? Since delta E is not tied to any deformable rod or bar, so how can we solve this? Okay, if you have figured out delta AB and delta CD, so you will be have some kind of similar triangles. So based on geometry, you'll be able to solve delta E. So let's see later how can we find out these kind of similarities. So the first step will be finding out these two forces, right? So what is FAB and what is FCD? So how to find out these two internal forces? Free body diagram. Okay, the free body diagram has been shown here. So let's use it to solve these two internal forces. So the first step would be free body diagram. The diagram is here. Right, so based on it, we can get several equilibrium equations. So sum Fx is meaningless since you don't have any force along x direction. So we will start from sum Fy equals 0. Right, from here you can get FAB plus FCD minus P equals 0. Okay, this is our first equation. Then the second equation will be, well, conveniently just select point B as the center and to count M about point D equals 0. Right here you have FAB, and P. Right, so they're in the same direction. Right, they will make moment in the same direction. Right, we will have FAB times its arm, that is A, plus P times B equals 0. That is our equation 2. Right, from equation 2, we can derive that FAB equals negative PB over A. That is negative 30 kilonewton times 0.4 over 0.2. That is negative 60 kilonewton. So FAB has been solved. Just from equation 1, then FCD will be P minus FAB. 30 minus negative 60 will be 90 kilonewton. Okay, so now we can calculate these two deformations. Delta AB will be FAB LAB over EAB AAB. FAB is negative 60 kilonewton, right? 1,000 times LAB is 0.3 meter, right? So that is 0.3 times 1,000. Transform it into millimeter, right? Over 70. So AB is aluminum, right? 70 giga-PA times 1,000. Transform it into MPa, and times cross-section area. That is 500 square millimeter, right? So from here, we will get negative 0.514 millimeter. What does this mean? If delta AB is negative, meaning that point B will move downward or upward, AB will be shortened, right? So point B will go upward. We can also calculate delta CD, that is FCD times LCD over ECD times ACD. In the same way, we will have 90,000 times 0.4 thousand over 200 giga-PA times 1,000 into MPa times cross-section area. This is 600. Okay, so here you will get positive 0.3 millimeter. So what does this positive mean? Meaning that CD will be elongated, so point D will go downward. Okay. So we have determined these two things. Then the rest work will be, so here, if you want to answer the first question, what is the deflection of point B? Right, this, of course, here the delta B will be what? Will be the same as AB, right? It's a point B deflection will be 0.514 millimeter upward. Okay, the third step, let's see how to determine delta E. Okay, so we have determined that along this bar, we have a this is point BDC, BDE, right? It's a BDE here, right? So the AB, the point B will go upward. This is delta B, and the delta D is downward. Here is delta D. Right. Since BDE is a rigid bar, so the shape will never be changed. It will still be a straight line. So we can connect these 2 points. You get point here. So this you will have delta E. Okay, so here you have delta E. And here is A. Here we have B. Right. So can we write the equation? Can we write the equation to find out the delta E? Well, you can find a lot of similar triangles, right? Several similar triangles. But how can we solve it? So here, using AB, you cannot solve it. We have to find out an additional length that is here. What should this x be, right? So now let's look at these two small triangles. Right, this is the first one. This is the second one. These two triangles are similar to each other, right? So based on these two, we can solve the x. Right? You can list that delta B over x equals delta D over A minus x. Okay, so this is 0.514 over x equals 0.3 over 200 minus x. Then here the x can be calculated as 126.3 millimeter. Then we can write another equation. Here just this small triangle is similar to this bigger triangle. Right. So this equation, based on the similarity, will be written as delta AB over x equals delta E over A plus B minus x. Okay. So from here, you can derive that, you can solve it. Delta E is 1.928 millimeter downward. Okay. You can see in this process, we will not use negative sign anymore, since this is a geometric problem. So negative signs is meaningless. Okay, so we will not use any negative numbers like negative 0.514. We just use positive numbers. They're absolute values.